Hi there. Here at the Precision Motion Control Lab under Professor David Trumper, we have been developing portable control teaching labs using the National Instruments myRIO system. Let me first introduce the Thermo-Lab, which is used as an introductory lab for teaching feedback control. In this lab, students build a portable thermal lab to learn the various ways to control temperature, such as on-off and PI control. As shown in the schematic, the thermal plant is a simple transistor circuit. The analog output from the myRIO modulates the collector current, thereby generating heat. The temperature of the transistor is measured by a thermistor, which is packaged together with the transistor in transparent heat shrink. First, students manually control the temperature by turning on and off the control effort. Here we can see the measured temperature rise when the control effort is set high and then fall when the control effort is set low. The goal of this lab is to have students get familiar with the dynamics of the thermal plant and also discuss why on-off control can be effective for slow dynamic systems such as thermostats and ovens. Next, we switch to automatic on-off control. Here the controller automatically turns on and off based on the specific threshold. Students can change the deadband amplitude of the on-off control and observe the result. Initially, we see the deadband amplitude of 0.1 degrees Celsius. Now we can see the deadband is removed, which in turn increases the frequency of switching. In this lab, students also try to manually control the temperature as if they are the controller. As students repeat controlling the thermal system, they begin to predict what the control effort should look like. In this way, they can feel the low-pass nature of the thermal system and begin to develop intuition for basic feed-forward control. The thermal lab concludes with a PI controller. In this lab, students can change the proportional gain and the integral time constant to see performance changes. With their final controller, students can test the step response of their closed-loop system. Also, they can trust the transistor with their finger to apply a disturbance and see how the controller compensates for this disturbance. This physical interaction makes students more interested and motivated to study control. Another tool we have developed for the myRIO is a DSA, or Dynamic Signal Analyzer. A DSA is a device that generates a system's Bode plot. A Bode plot provides insight into the dynamics of a system and aids in the development of a controller. Without a DSA, generating a Bode plot requires exciting a system with a function generator and measuring the system's response at a given frequency with an oscilloscope, or purchasing a dedicated DSA. This video shows the DSA generating the Bode plot of a double mass spring damper demo we show in class. By giving students a DSA, they are able to 1. Verify the behavior of physical systems at multiple frequencies, 2. See deviations from theory, such as the effects of time delay, 3. Design controllers for physical systems from data of the physical system, not just theory, and 4. Test how their controllers will perform on real hardware. DSA works as follows. First, it generates checkpoints to keep track of the current frequency of progress. Second, it generates a swept sine wave to excite the system at each of those frequencies. Then it checks if the transient from frequency switches has died out, and then for each frequency, records the system response at 2 points and calculates the quotient of the two magnitudes and the difference in the two phases of those signals. And finally, it plots the system's magnitude and phase. Students can use the DSA at the same time as a controller. The controller is contained in block 1, while the DSA is contained in block 2. This allows students to measure the frequency response of the plant, the controller, of the return ratio or open loop, of the closed loop system, and of sensitivity. In addition, we have developed a lab for exploring the effects of digital control. For the lab, students work with a double integrator op-amp circuit, the electrical analog to a mechanical free mass. This allows them to implement discrete time modeling and controller design. They understand the effects of sampling and quantization on the control loop, in addition to the effects of measurement noise and disturbances. Here we can see the DSA being utilized to generate the frequency response of the double integrator. Since the double integrator is implemented with inverting op-amps, the phase is increased by 180 degrees. In addition, a social sampling rate is used to show the effects of time delay. Here we can see the differences between modeling a system in continuous time and in discrete time at multiple sampling rates. We see that the discrete models capture the effects of time delay, as shown in the measured response, whereas the continuous time model does not. Here the top two figures show the step response for the double integrator plant with a PID controller for a sampling rate of 50 Hz. The two figures below show the same plant controller step response with a sampling rate increased to 100 Hz. We see the step response appears staircase-like due to the effect of the zero-order hold. Students also learn how changing the sampling rate affects the control design. Both setups use a controller designed for 50 Hz sampling rate, yet the second setup uses a 100 Hz sampling rate. This causes the step response to be less damped than designed for. Here we have the Flex Lab or Lev Lab system, which is a portable mechatronic system on a single PCB. A cantilever bronze beam with two permanent magnets makes up a spring mass damper plant. This is actuated by a Lorentz force actuator consisting of a 4-layer, 80-turn spiral coil embedded within the PCB and powered by a linear amp. The position of the magnet is measured by two Hall effect sensors mounted vertically on both sides of the coil. Here we see the open loop system is very lightly damped. This video shows the open loop step response of the system where the coil currents are square wave signals. Due to the light damping in the system, we see the beam's vibrations take a relatively long time to decay. The figure on the left shows the Bode plot from the coil voltage to the magnet's position. The blue circles show the measured data using the DSA, and the green line shows the modeled Bode plot. The right-hand figure shows the open loop step response of the system. We can see that the system has a damping ratio of about 5 thousandths. Students in the class can work on modeling, system identification for the system, and then design a controller to better damp the system. The video shows the flexible beam system in closed loop control with a crossover frequency of about 30 Hz and a phase margin of about 40 degrees. We can see that the beam is much better damped in closed loop. The FlexLab system can also be used to demonstrate self-resonant control, which is an important building block for tapping mode control of atomic force microscope probes. Self-resonant control is implemented by adding positive or negative damping to the system to keep its poles on the imaginary axis. When the system has poles on the left-hand side of the imaginary axis, the controller can inject negative damping. When the system has poles on the right-hand side of the imaginary axis, the controller can inject positive damping. Here we can see the self-resonant control used causes the flexible beam to oscillate or tap at its natural frequency at a constant amplitude. Lastly, the board can also be used for magnetic suspension when the flexible beam is removed. Here, a spherical permanent magnet is magnetically levitated by the coil in the PCB, and the magnet's position measured by the Hall sensors are used for feedback. This magnetic suspension system is unstable in open loop, but can be stabilized by means of feedback control. Thus, students learn how to model an inherently unstable system and then design a controller that stabilizes it. Thank you for your time, and we hope you can find use in these labs.